Okay, how not to use OAuth, or maybe also how to use OAuth. So let's start. Well, this is not working. I think it's not working. Okay, it's working. Okay, let's start with this question. Who in this room is familiar with OAuth? Like all the details? All the 4 grant types? Okay, and when I'm saying OAuth, I'm talking about OAuth 2.0. So we're not talking about the older ones here. Okay, so OAuth 2.0. Let's get everybody on the same page and start with a brief usage example here. So we have a user, and she'd like to authorize some online photo editor app to access her photos at Google Photos, her Google Photos account or whatever. So in OAuth, the photo editor app would be the client, and Google Photos would provide the authorization server and the resource server. Now, OAuth OAuth knows 4 different grant types. And the most important one is the so-called authorization code grant type. And this works as follows. First, the user says, OK, connect the photo editor app to my Google account. And then the photo editor app, here acting as the OAuth client, will create an authorization request. That will be sent to the user, and the user's browser will be redirected to the authorization server of OAuth. In the next step, Google will ask the user, do you want to give access to your photos to the photo editor app? And the user, of course, needs to authenticate to her Google, needs to log into her Google account, and then can give access to her photos. And then an authorization response is created. And this authorization response in the OAuth authorization code grant type contains a so-called authorization code, which is then redirected back to the client. And the client now can use that code to send the so-called token request to the token endpoint, and it sends the code, and it gets back the access token. And the access token is the single most important thing in all OAuth flows, because it's what gives access to the user's data. So with the access token, you can do whatever the user granted you to do. That's exactly what the client will do in the next step. OK, so this is the authorization code grant type. We see the important things here, the authorization code, the access token, and of course, there's a lot of checks going on in the background. For example, we here have a so-called redirect URI parameter. That parameter is used to determine where the authorization response is being sent to. Of course, we don't want that response to go straight to some attacker, and therefore, there's a check at, in this case, Google, that checks whether this client is using that URI for OAuth. So it has a list of redirect URIs or a pattern of redirect URIs, and then it checks the redirect URI here, and if it passes, then it will redirect the client, the user back to that client. There's also another check, the so-called state parameter here. It's filled with some random nonce. And in the request, so this is created by the client, in the request, it just puts some random number there. And this is returned by the authorization server. And if it's not the same number appearing here, then the OAuth flow is aborted. OK? And another thing we can optionally have here, so-called client authentication. The client might need to provide some credentials to send the token request. We need all these details later because we're talking about how to make OAuth more secure. And then there's also another important grant type, and it's called the so-called implicit grant. And the implicit grant starts similar, but works a bit different starting in the authorization response. We see in the authorization response there are no query parameters added here, but instead, in the fragment part of the URI, there's an access token. So no authorization code used here. Instead, an access token is created immediately in the authorization response. So the browser is redirected to that URI, for example, client.example/auth-OK. And the browser will now retrieve that URI. So that's a location redirect. The browser will retrieve that URI, and the browser will do so without sending the fragment part of the URI to the server. That's just how browsers work. So the fragment part is never sent to the server. But the server can return some JavaScript, and that JavaScript now has access to the access token. And it can either use it directly and just send it to the resource server and get some photos from Google Photos or whatever, or it can pass it to the backend, and then the backend can use the access token. So this is the implicit grant. So who uses OAuth? Well, almost everybody does. It's everywhere nowadays. So it was standardized in 2012 by the IETF in RFC 6749 and RFC 6750. And since then, we've seen a tremendous adoption across the industry for authorization and also for authentication, so OAuth itself is not intended to do authentication, but you can do authentication with OpenID Connect. And OpenID Connect is based on OAuth. It's essentially OAuth plus some extras. And for example, Google Login uses OpenID Connect. And the key success factors were simplicity and versatility. You can use it for almost everything. But is it also secure? Well, let's see. Let's start with the OAuth implementations. So with clients, authorization servers, and resource servers. And if you look at the existing research in that area, and also, so this is also confirmed by what you experience when you see the implementations, many implementations contain flaws. For example, we see many implementations that don't properly protect against cross-site request forgery. Even the 25 in the OAuth clients in the Alexa top 10,000 websites, 25% of them don't manage to prevent cross-site request forgery properly, which is a lot. Also, there have been vulnerabilities even in official SDKs, for example, by Facebook. And of course, in the beginning of the year, you might have heard about the big Facebook hack. That was essentially also caused by an OAuth implementation bug. Okay, so implementations have a lot of flaws. But what if you have an excellent implementation? If you follow RFC 6749 and all the others perfectly, is it secure then? Well, there's a lot of security advice in the two RFCs I already named, and the third one, the OAuth threat model, RFC 6819. But still, OAuth has a lot of, or faces a lot of challenges. We have a complex and evolving environment. So 2012 is 7 years ago. Many things changed since then. And we see OAuth being used in new applications that we didn't see or that nobody even imagined in 2012. So what are the challenges that OAuth faces right now? Let's start with the first one. Implementation flaws. We talked about that. We still see a lot of them, and they are always the same. So people always are doing always the same mistakes. For example, insufficient redirect URI matching. So the code or the access token is being sent to an attacker very easily. Or the state parameter is not used properly. So the state parameter is intended to protect against cross-site request forgery, and in RFC 6749 and 6819, it says you have to put a random number there, and it's a fresh random number, and then you check it when you get it back, and people are not really following that. And then technology changed. For example, the URI fragment handling, so how the fragment of the URI is handled when a browser gets a redirect. This behavior has changed since 2012. And the OAuth standard needs to kind of adapt to that. And that can actually lead to a vulnerability when it is used together with an open redirector. So what's an open redirector? Well, very simple. It's a parameterized, unchecked redirection. So say, for example, you have a URI like this, client.example / anything, whatever, and then a parameter resume at, and then you can provide some URI. And if you call that URI, then it will redirect you, it will send you a location redirect header to that URI. So how can that be exploited? Well, let's look at an example again. So here we have more parties than before because we have on the right an attacker. And that attacker now redirects a user to that URI. So example.com/authorize, and the redirect URI, which of course needs some URI encoding, is client.example/auth resume at evil.example/harvest. So what happens now? Well, the user, or the user's browser rather, follows that redirect and ends up at the authorization server. The authorization server now probably checks the redirect URI and sees that it points to client.example/auth. So everything's fine. It points to the client. The token will be redirected to the client. The user authenticates, consents to the authorization, and so on. And we are in the implicit flow here. So the authorization server will create an access token and put it in the fragment part and redirect the user back to client.example/auth resume at something, and then the access token. So what happens next? Well, the browser goes to client.example/auth resume at something without sending the fragment here. And then the open redirector comes, sends a location header to evil.example/harvest. And now what happens is the following. The browser will call evil.example/harvest and attach the fragment to that URI. So the attacker can use some JavaScript, so that is not sent in the GET request, but the attacker can just use some JavaScript to harvest that token. So how did that happen? Well, in 2012, this didn't happen, because in 2012, the browser would not have reattached that fragment part to the URI after the location redirect. So this is an example of how technology changed and make that protocol that used to be more secure, less secure. So technological changes can cause implementation flaws. Next challenge, high-stakes environments. Originally, it was anticipated that OAuth would be used to give access to your photos like we've seen before, for Facebook or whatever, but not maybe for open banking. But nowadays, it's used for open banking. Across the EU, we have the PSD2 regulation, which forces banks to implement interfaces for third parties to their users' accounts. And most of the standards that we see, like Open Banking UK, STAT in France, the Berlin Group, and also OpenID Financial Grade API, they all build on top of OAuth. And there are many more that I didn't even put on here. I think every open banking API that we are seeing in development now is based to some degree on OAuth. And most of them just say, use RC6749. And then you're done, you're safe. And you're not. So that's a big problem. And we also see other applications like e-government, mobile operators. The Cloud Signature Consortium is building a technology to create legally binding electronic signatures just based on OAuth. We also see e-health applications. So a lot of, a wide range also of high-stakes environments. And everybody's using OAuth, and most of them just say, yeah, just follow RFC 6749, and then you're done. Okay, so we have a completely different threat model here. I think that's pretty obvious. Next challenge, dynamic and complex setups. Originally, in 2012, again, it was anticipated that OAuth was used like this. So we have one client, and that one client is configured with to connect to one authorization server and maybe one or more resource servers. And this relationship is configured statically, and they kind of trust each other. So everybody's trustworthy in this setup. But this is not how OAuth is used today. Today, it looks more like this. We have one client connecting to many authorization servers and many resource servers. These relationships are built dynamically. So maybe a user comes and says, I'd like to use that authorization server, and then your client has to connect to that authorization server, depending on which ecosystem we're talking about, but these setups exist. So many participants, and some of these can, of course, be not trustworthy or less trustworthy than others. So we have a completely different setup. We have dynamic setups, dynamic relationships. We have multiple AS, multiple resource servers, and so on. And this exactly is where new attacks appear. And one of these attacks that appeared was the authorization server mix-up attack. I'm not going to talk about the details of that attack here, but the interesting thing here is how it was found. Because it was not found by the standardization body, and it was not found during pen testing or whatever. It was found using a formal analysis. And this is an interesting thing, because this attack might teach us how to find similar attacks in different protocols on the same protocols in the future. So let's briefly talk about formal analysis. So what does it mean? As a practitioner, you might not have a precise picture of what formal analysis is. So I will try to give you an idea of how that works. And formal analysis means you build a formal model of some system, and then you do some analysis on top of that. So essentially, you can do offline testing of your application logic, or in the case of OAuth, of your standard, of the logic that is built into the standard. You can do that before even writing a single line of code. So it's not static analysis, it's not dynamic analysis, it's analyzing the logic behind the application. And this can help us to find regressions, as we have seen before, in the caused by technological changes. And this has actually successfully been used for cryptographic protocols for many years now. But we are not used to have that on the web right now. But if you think, for example, of TLS 1.3, this standard was developed together with many people of the formal analysis community, and they provided a lot of input. They really try to make sure that this is a very, very secure protocol. And if you do this, it will also help you to precisely define what you mean when you write a specification. So you also have this benefit of getting a better specification if you use formal methods. Okay, and last but not least, it also can provide you with security guarantees, of course, within the limits of the model. So this is not common for web applications or web standards yet. But how does it work if you want to analyze a web application or web standard, say OAuth? Well, on a high level, it looks like this. So you start with a generic description of how the web works. Okay, that's a lot to ask. But you can boil it down to what is relevant for security. So most of the time, we're not caring about whether it's a cat picture or a dog picture. So you don't need to talk about user interface details most of the time, for example. But you need to define how a browser works, at least on some specific level. You need to define how a network works, and so on. You create a formal description of that. So you write it down in some formal language. You can use a tool for that, or you can just use pen and paper. And then on top of that, you build the application-specific model. So you take the standard, for example, the OAuth standard, and then you define what's written in the standard, essentially. You say, how is an application using OAuth behaving? What does it do? What methods of the browser does it invoke? What JavaScript does it use? And so on. Then you have all the tools you need to precisely define what security means, which is often not as easy as it sounds, because intuitively you know that with OAuth, nobody else should be able to, I don't know, access your Facebook account. That's pretty clear. But if you want to define that precisely, it's not so easy. But you can now do it. You have all the tools. And then you can try to prove that your application is secure and you're done, right? No, of course not. In an ideal world, this would work, but it will not work like this. Instead, you will not be able to prove that, because you will find an attack, most likely. You will find an attack, one or more, but the good thing is you found an attack. And now you can try to fix that attack, and of course, then integrate these fixes into your model again, and then you can do the same thing again. And then rinse and repeat until your proof goes through. And then you've found some attacks, and ideally, you also have a proof within the limits of the model of the security of your application. And this is exactly what I did in my PhD thesis for OAuth, and also some other things, but we're talking about OAuth today. I created the so-called web infrastructure model, which is just a description of how the web infrastructure works. It's a manual pen and paper model, so it's not based on some model checker or any other tool, because I wanted to create a very comprehensive and precise model of how the web works. And this model contains browser behavior, scripts, windows, documents, how different documents can interact with each other in a browser, and so on. There's also an abstract model for DNS, for networks, and so on. So it's a very comprehensive model. We have a lot of features in there. And using that model, I created a model of OAuth 2.0. So I just took RFC 6749 and all the other security recommendations out there to build a model of OAuth with all the security features that were known to date in place, because I was not interested in finding any attacks that we already know about. Then in the next step, I provided detailed definitions for authorization, authentication, and session integrity, where session integrity covers things such as session swapping attacks. And then I tried to prove the security. And I failed, because I found attacks. Attacks like the 307 redirect attack, various attacks on session integrity with the state parameter and similar things, and the AS mix-up attack. Again, I'm not talking about the details of the attacks, because we're not on an attack conference here, but we're interested in how to defend. I then developed fixes against these attacks, integrated them into the model, and was able to prove the security of the OAuth protocol, again, within the limits of this model, of course. Okay, the AS mix-up attack. Very briefly, you confuse the client to send the user to an honest AS. So the user goes to Google and gives authorization. And then the client still thinks that the user doesn't go to the honest AS, but the client thinks that the user goes to your own AS, so the attacker AS. And therefore, the client sends the code and the token to the attacker. If you're interested in details of this attack, we can talk about that after the talk. The fallout is interesting of the AES mix-up attack because it kind of inspired a new security workshop series, the OAuth Security Workshop. Jim was there a month ago in Stuttgart. This is Jim. And more importantly, we created a new ITF RFC, the OAuth Security Best Current Practice. And that is a new document that essentially updates all the security best practice you know for OAuth. It's currently under development, but we hope to finish it soon. And it doesn't replace, but it complements the existing security advice you get for OAuth. The main features are an updated and more comprehensive threat model to account for these high-stakes environments. We have a description of the attacks that are known now, that were not known back then, and we provide simple and actionable recommendations. Okay, so the 7 most important recommendations in the OAuth Security BCP. I see in this conference today, we see a lot of 7 things talks. Let's see. Okay, first one, most important one, do not use the implicit grant any longer. Thank you. While it is perceived by many as being the simpler OAuth, it is mainly the more insecure OAuth, so don't use it. It has so many problems and doesn't provide any defense in depth. For example, the access token is contained in a URI. URIs can leak from or they are in your browser history, they can end up in proxies, they can be locked by operating systems, and of course, the access token being available to the JavaScript here makes it susceptible to cross-site scripting. So this is kind of dangerous. At the same time, you can't really protect against access token replay. Anybody having this access token can use it. You don't have any sender constraining for the access token. Then, access token injection. So at this point, an attacker can just use some access token he got from some other flow and inject it here, and then the client will use that access token. The client cannot check the origin of that access token, essentially. So the implicit grant sends this powerful and long-lived access token through the browser, which is not a good idea. It lacks features for sender constraining. We have replay and injection problems, and it doesn't provide any defense in depth. So if any of your defense lines falls, then you're screwed. So why is it even there? Well, because back in 2012, we didn't have cross-origin resource sharing, so it was hard to do the token exchange where you send the code and get back the token. Therefore, we had this simpler option for OAuth, but this is not needed in 2019. Don't use it. This is exactly what the new BCP says. Clients should not use the implicit grant. This is a should not for political reasons. Clients should instead use the response type code, so the authorization code grant type. Okay, next one, use instead the authorization code grant. But don't use it like it was written in RC 6749. Instead, use modern security features that we have for the auth code grant. For example, PKCE, proof key for code exchanged. This means it's a very simple mechanism, actually. So in the authorization request, the client sends a so-called code challenge. That is the SHA-256 hash of some random number. And then the authorization code that is created here will be bound to that code challenge. And if anybody wants to use that code, he has to provide the code verifier, which is just the plain text, so the random number that was hashed before, which nobody can know because this was the hash, and therefore nobody can use the code except for the original client. And the funny thing is, this does not only provide you with replay and injection prevention for the authorization code, but instead also provides you with cross-site request forgery protection, if you think about it. So, nice feature. Second one, you can make code single use. So anybody replaying this whole request cannot just get a new access token. And also a very important feature, you can use the authorization code grant to sender constrain your access tokens. How does that work? So it's very simple. You use TLS client authentication with a client certificate that is just self-signed, so no PKI in the background, just a self-signed client certificate. And the client sends that certificate in this connection. The server will then bind this access token to the client certificate, and anybody using that access token has to present the same client certificate. That's OAuth token binding using mutual TLS, and it's a very good mechanism for sender constraint tokens. So to sum up, authorization code grant with PXE, proof key for code exchange, and MTLS protects against injection and replay. We have defense in depth because we have many lines of defenses. And this is exactly the recommendation that is contained in the security BCP. You must use PXE if you use the auth code grant, and you should use TLS-based method for sender-constrained access tokens. Okay, this is the first and most important recommendation in the new BCP. Second one, prevent mix-up attacks. We have seen not many details about the mix-up attack, but it's very simple to defend against the mix-up attack. The client must be able to see where the authorization response came from. And this is simple to accomplish. The client needs to ensure that for every AS it is using, the AS uses a different redirect URI. So the client exactly sees from which AS a response comes, the authorization response comes. You get that for free if you're using OpenID Connect. You just have to check it. And the client must keep track of which AS was intended, and then ensure that only this AS can send the authorization response. Third recommendations, stop redirections gone wild. We still see that many people don't get this right. So they use, for example, pattern matching for redirect URIs. And this always goes wrong for some reason. People don't get their regular expressions correct, and they use wildcard all over the place. So just don't do that. Instead, use exact redirect URI matching. Use one redirect URI per AS, and this redirect URI is the one, and no dynamic things, just one redirect URI. And do not use or do not build open redirectors. So if you want to redirect based on some URI parameter, then use a whitelisting or use some means of authentication for that URI. Okay, fourth one, prevent CSRF attacks. That's not a new one, but so already in the old RFCs it says use the state parameter. But as I said before, if you use PXE and the client and the authorization server both support PXE, then you get CSRF protection for free. So you don't need to use state any longer. You don't need to think about random numbers, just except for the one for PXE. So do that. So use PXE, then you don't need to use state any longer. And then you can use state for its original purpose, namely just some application state. Okay, fifth one, limit the privileges associated with access tokens. We have seen sender constraining so that not anybody can send the access token. You should also do receiver constraining. Limit the access token to be valid at one single resource server only, so that if one resource server becomes compromised, it cannot just use the access token somewhere else. And of course, try to reduce the scope and the lifetime that is associated with an access token, with each access token. To do that, you might want to use refresh tokens, which you can use in the authorization code grant. Refresh tokens are not a new concept, but they are a great concept. They are very simple, so each time you get an access token, you also get a long-lived refresh token. And if your access token expires, you can use the refresh token to get a new pair of access token and refresh token. So the access token can be more limited in its scope and in its lifetime, and you can throw all your protection mechanisms on the refresh token. What are these? Well, you can use client authentication, client binding. You can say only this specific client that needs to authenticate can use the refresh token. You have a sender constraining mechanism just like for the access tokens, and you can use refresh token rotation. So each time so we've seen before, you get a new refresh token each time you use a refresh token. But if anybody is using an old refresh token, you immediately invalidate all the refresh tokens and all the access tokens associated with that brand. So if somebody tries to replay a refresh token, everything will be torn down essentially. Seventh and last, do not use the resource honor password credentials grant any longer. This is, it's really strange. So it works as follows. The user sends a username and password for the AS to the client, and the client uses that username and password at the AS to get an access token. I think the downsides are obvious. So the client sees the username and password of the user. This is completely orthogonal to what you do with two-factor authentication, so it's hard or impossible to integrate. And it was only meant as a stopgap solution for migrating to OAuth. And it's a really long grant name, even for German. So what else? This was the last one. We have a number of smaller recommendations. Do not use the HTTP 307 redirect. Prevent code leakage and from referrer headers and other sources. Use client authentication if possible, and some others. So if you're using OAuth, I advise that you look into that document. It's a draft right now, but it's already quite complete, I think, and yeah, it's maybe 90%, 95% done. To sum up, we have seen that OAuth implementations are often vulnerable. We have seen that in practice and in research. The OAuth protocol definitely needs an update regarding the security guidance to protect against new attacks, to protect it in high-stakes environments, and to adapt it to the evolving web environment itself. We have seen that formal analysis can be helpful, although it's not widely used right now, but it can be very helpful, especially in standardization, to find attacks, test solutions, also to find regressions potentially. And all of this ended up in the new IETF OAuth Security BCP, which addresses new and old security vulnerabilities and provides actionable solutions. So that was my talk. If you're interested, come talk to me about details of the attacks and the mitigations, the formal analysis, of course. If you're interested to join us at the OAuth Security Workshop, we don't have a date yet for the next year, but we will soon. And of course, we are looking for developers with a security background at yes.com. Thank you. Okay. Okay, how does a high-stake environment change the threat model of how OAuth, or in other words, why is the current implementation not sufficient? Let's go back. We don't have to. Okay, that's fine. So in the high-stakes environments, we have a problem because we don't have a problem per se, but we have a new situation where, for example, we have to assume that some resource servers might become compromised. So this might be a bank, but this resource server might be one branch of the bank or something like that. So it might be loosely coupled to the bank. But still, if that resource server is compromised, it should not be able to use the same access token at a different resource server at the same bank. And with the old OAuth security model, that would be possible because we don't have the receiver/sender constraining of the access tokens. That's, for example, a driver for the security advice on the sender and receiver constraining of the access tokens. And we have similar situations like this. Also, for example, regarding TLS connections, again, in banks that have to be broken up or something like that, so you need to provide an additional layer of security at different points in the protocol. One more? Okay. Okay, that's a good one. How complex is the web infrastructure model for the formal analysis? Even same origin policy is nowhere specified and has a lot of quirks and corner cases. This is exactly why it's complicated to build a web model. But it's also very interesting. So the model is very complex, to answer the first question. It fits on, I think, so it takes like 40 pages in my thesis, plus a lot of explanation. And it's nothing you can just take and build something on top of that, because currently it's too complicated. And that's also what makes it too complicated to put this into some tool, but we're working on it. So I'm not working on it, but my former colleagues are working on it. You have, even if you don't look at all the corner cases, you have a lot of complexity. You need to read like a few hundred or maybe 1,000 pages of specifications like HTML5 and many, many other things. And some of these are not documented anywhere. Some of these you just have to test in some web browser. The good thing is in a model you can really take into account different behaviors. You can just say, okay, I'm not sure what's happening here in this case. Let's just say anything happens, or within some limits, anything happens. And then you can actually work with that in a model. So it's not a software product in this sense. But yeah, it's very complex. And some things like same origin policy corner cases, you just have to test, or you just have to assume the worst. In a model like this, you can also sometimes just assume that no security exists. So assume the worst and then see where it leads you from there.